In this chapter, we will be introduced to the concept of organic synthesis. This is really one of the neatest parts of organic. Once you learn all these reactions, etc., you're able to take them and use simple starting materials to construct more complex molecules. And that's what we call synthesis. So let's go ahead and get started. We talked about hybridization in carbon. Once again, we said that carbon really likes to form 4 bonds. If we have sp3 hybridization, it's called, that's 1 s orbital and the 3 p's, all hybridized to form tetrahedral geometry. Our bonds are all equal, they're single bonds, nice free rotation around all of these single bonds. sp2 hybridization, we said we take 1s and 2 p orbitals, we make 3 bonds for a trigonal network, and that leaves 2 p orbitals left over. These overlap to form what we refer to as a single or as a double bond. Double bond has hindered rotation because the orbitals must align with each other in order to form the pi system for our double bond here. Triple bond sp, so that's 1s and 1 p, and we'll see when we build this, we're going to take our s and our p. 2 orbitals will form 2 sigma bonds. This obviously leaves 2 p orbitals available on each of the carbons. Each of these has 2 p orbitals. They're oriented at right angles to each other. And so putting them in, it would look something like this. Now, just like with alkenes, once these orbitals are in position, they can overlap top, bottom, and on each side, and we form 2 sets of pi bonds. This one's a side, this one's on the top, with our sigma network down the middle. Each of these is referred to as a pi bond. We show it as 2 additional bonds between our carbons. Is there free rotation around this? Well, probably not, but you really can't tell because this is a linear system, isn't it? Theoretically, if we had rotation around there, we would disrupt this pi system. Oh, the pi system is fairly uniform. The electrostatic potential map here looks something like this. And again, you can see this huge belt of electron density around our triple bond. Just like with alkenes, this belt of electron density is going to be the source of all the reactions. Things are going to come in, they're going to interact with this electron density, and we will get addition reactions. Whenever we have a new functional group, the first thing we get to do is to name it. Just like with alkenes, we want to choose the longest chain, but it must contain the alkyne. That's rule 1. When we number our chain, we want to give the first carbon of our alkyne the lowest possible number. Our suffix here is going to be yne. If we have more than one, we would call it diene, triene, etc. For this little molecule right here, we look and we see our longest chain containing the alkyne is going to be 1, 2, 3, 4, 5 carbons long. So that's our parent chain. Our second rule we want to give it is give the alkyne its lowest possible number. Therefore, we want this to be carbon number 1, 2, 3, 4, 5. And finally, we look at substituents just like we do with everything else. Here in carbon number 3, we have an ethyl group. Therefore, we would name this thing, it's a 1-pentyne. At carbon number 3, we have an ethyl group. And so the acceptable name would simply be 3-ethyl 1-entine. Any questions? Now, quite often, especially in naturally occurring products that have triple bonds, you will have mixtures of double and triple bonds together. An example of this might be something like this molecule. Because of the mixed functionality, you have to have a rule. If there is no difference in the numbering between the double bond and the triple bond, then the double bond will have the lowest number. So the alkene has precedence over the alkyne. As we do other functional groups, you'll see that there are precedent orders. Here, double bond wins over the triple bond. So we would number this guy starting down here. Our double bond would be between carbons 1 and 2. Our triple bond between carbons 7 and 8. Coming up with a name here, we have 8 carbons. It's an octene, but we have an alkyne here in carbon 7. We start off just knowing that it is an alkene or octene, 1 octene. But we have to somehow say that we have our triple bond here in carbon 7 and 8. The way we do that is change the ending here, drop our E off. We'll put in the location of our triple bond, so this is a 7-ine now. 1 octene, 7-ine. Again, we drop the E and then put in the location of our second functionality. As we do lots of different functional groups, you'll see that this shows up a lot, where we have to show the functional group and its location at the end of our name. Now, if we change things just a little bit and moved our double bond in, now there would be a difference in the numbering. When there is a difference in the numbering, the alkyne would get the lowest, because this will be a 1 versus 2. So this is going to be carbon 1 now. And our double bond is here between 6 and 7. When we construct the name, this is going to be a 6-octene, that's down here, 1-ine. Now on the exam, I probably won't ask much in the way of nomenclature where we have mixed functionality, but again, especially in natural products, you do see a lot of this thing. An example of that. Take a look at this. It's an alcohol. Has a chiral center, as you can see, has 2 triple bonds, 3 double bonds, another alcohol functionality on the end. As you can imagine, naming this might be a little bit tricky. Note the very nice, long, straight section here as you do this. Kind of cute. This is hemlock. It's a very toxic substance. This is the stuff that they made Socrates drink to execute him. So, but we're not going to name stuff like that other than to call it hemlock. Any questions on the nomenclature? Your exam will have a page of nomenclature, just like it always does. A mixture of alkene and alkyne nomenclature. For the alkene, make sure you know the easy cis strands nomenclature. Alkyne, there's obviously nothing to do with cis strands. All right. a number of reactions of alkynes that we're going to talk about. Now this might seem a little overwhelming because we just had a lot of reactions of alkenes. But what you're going to see here is that these are basically the same types of reactions. And once you understand the alkene reactions, these are going to be trivial. We talked about addition of halogen acids, HX, to an alkene. We know that in an alkene we had Markovnikov regiochemistry. Well, we see exactly the same thing here. Instead of adding 1 mole of HX, we're going to add 2. And again, the halogen is going to go to whichever carbon of the alkyne would give the most stable carbocation. So we'll call that Markovnikov. The addition of halogen, X2, just like with the alkene, except twice. So instead of a 1,2 dihalide, we have a 1,1,2,2 tetrahalide. We can hydrate the thing. Now this might seem like magic. We're going to hydrate it 2 different ways, one with just mercury and acid, one with BH3THF, just like we did with alkenes. This gives Markovnikov, this gives anti, just like with alkenes, except that the product isn't an alcohol. It's actually going to be a carbonyl. We'll see why that happens. The reason is we form what's known as an enol, but we'll do that in a few minutes. We could reduce it all the way down to the alkane. We can do a poisoned catalyst, it's called, where we only reduce half of it. Again, our hydrogens will go in cis, and we wind up with a cis alkene. We can do dissolving metal reduction and actually wind up with a trans alkene. And finally, this is an SN2 reaction. SN2 reactions are covered, I think, in chapter 11, but it's a very simple one here. All we're going to do is form the alkyne anion and do a nucleophilic displacement. The way this works, alkynes are acidic. Now, they're not acidic in the way that we think about strong acids being acidic. But when we say an organic compound is acidic, that means that it can form an anion that has a reasonable stability. In order to pull off the hydrogen here, we need a very strong base, and for this we typically use sodium amide. The way you make sodium amide is you take liquid ammonia and you add a chunk of sodium. Just like sodium and water will fizz and form sodium hydroxide, this fizzes and it forms sodium amide. So it's a sodium salt of ammonia, NH2, it's a very strong base. This will yank this hydrogen off, give us ammonia, and this is our anion paired up with the sodium cation. In the reaction, what happens is the anion, having lots of electrons, is going to be a nucleophile. Here we have a simple alkyl halide of some sort. The electrons from the nucleophile will attack the carbon. Let's go. They're supposed to. There they go. When they do, the iodine leaves, and we wind up with an alkylated alkyne. This allows us to take a simple alkyne and attach basically anything else to it. Works best with primary alkyl halides. We'll talk more about that in chapter 11. This reaction in general was covered in chapter 6, so you can review the SN2 mechanism, the substitution mechanism. The lab that we did last week was an example of an SN2 substitution. Of course I have a movie. This is our 3-carbon alkyne, so it's propyne. We've already made the anion, and it's going to attack chloromethane. Remember, in this type of reaction, we don't have an intermediate. We simply have a transition state where the nucleophile comes in, leaving group leaves, and this is a planar carbon. Wind up with our product, which is 2-butene and chloride anion. So let's go ahead and watch it happen. The nucleophile is going to come in. As it does, the leaving group will leave. And note the central carbon goes planar in the transition state. And that's really all there is to it. Very simple little SN2 reaction. Again, no intermediate, just the transition state. I guess it's not going to let me play it again. Well, we were lucky to get it to work once, I suppose. Any questions? All right, let's go ahead and talk about the rest of our simple addition reactions. We know that if we took HCl and we added it to an alkene, that we would form a chloroalkane. Well, we're going to do the same sort of thing here. We're going to ask the very same question whenever we see the conditions, and that is we'll look at the 2 carbons of our alkyne and we'll ask which one will form the most stable carbocation. This is a primary carbon on the end. This is a secondary carbon, so the secondary carbon wins. What happens is we're going to add 2 moles of HCl, and both chlorines are going to go on this carbon. There's a product. Again, it is a 1,1 dihalide. So we add the thing twice. The intermediate here is this guy. After we've added it once, we wind up with this alkene. Now, look at this alkene and ask yourself the same question. Which of these carbons is going to form the more stable carbocation? Well, this is primary. This is not only still secondary, but it has a chlorine next to it. Remember, the chlorine can stabilize by resonance. So this is really a very reactive intermediate, and the second mole adds very rapidly. Any questions? The addition of halogen. So this is chlorine, bromine, and iodine. Will once again be very, very similar to the reaction of alkenes. Whenever you see an alkene and you're adding halogen, you know that what you're going to do is simply add the halogen. Our addition would be trans. In this case, we would form this vinyl halide, trans vinyl halide, by the same mechanism that we always use. Once we have the vinyl halide, this adds a second mole of bromine. Again, they come in trans, but you can't tell. You just wind up with a tetrahalide. Again, it's referred to as a 1122 tetrahalide. So very, very similar. Both of these are very, very similar to what we saw with alkenes.
Yeah. Is the intermediate part of the answer?
I would not ask you to draw this intermediate. But looking at the intermediate, it makes real good sense to you, doesn't it? All right, let's go ahead and do hydration. If we have an alkene and we do of acid and mercury 2 acetate, we would form a Markovnikov alcohol with. Well, we're going to do exactly the same thing here. We look at the 2 carbons, decide which one of these is going to give the most stable carbocation. We have a primary and a secondary, so our secondary wins. In the presence of mercury and acid, we will add the elements of water, and we will get this intermediate. This is referred to as an enol. Now, in Organic 2, we will spend a very, very long time talking about enols, because enols are very important in reactions of carbonyl compounds. This enol doesn't exist to any large extent in this particular form, but what happens is this undergoes an internal rearrangement called a tautomerization, where we're going to take the hydrogen off of here and put it on this carbon. The product turns out to be the ketone. Now, again, this sounds a little bit like magic. How do you remember this for the exam? Simply look where the oxygen is, first of all. The oxygen is on our Markovnikov carbon, isn't it? Instead of forming an alcohol, we simply form a carbonyl. All right, how does that happen? This is what our enol looks like. This oxygen, the OH here, can lose a proton to a base. When it does, the electrons are going to move in to form our carbon-oxygen double bond. When that happens, that would be too many electrons on the carbon, so these will move out, and they'll pick up the hydrogen. The whole thing will look something like this. Once again, this hydrogen has effectively been moved from the OH down to this carbon. In this case, we get a CH3. This mechanism is something you do need to know. Like I said, in Organic 2, we're going to be doing lots and lots of reactions of carbonyl compounds. And many of these actually go the other way, where we're going to form an enol intermediate with electron density at this carbon. So we'll use that as a nucleophile. So this is a very important mechanism for you to understand. Any questions? Well, with alkenes, we said we could form Markovnikov alcohols by hydration with mercury. With an alkyne, you really do need the mercury. And we could form an anti-Markovnikov alcohol by hydroboration oxidation. We can do exactly the same thing with an alkyne. We're going to form an anti-Markovnikov enol, and the anti-Markovnikov enol is going to then rearrange or tautomerize to form a carbonyl. So we start off looking at our alkyne, and we decide which one of these is the Markovnikov carbon. Which one would form the most stable carbocation? We have a primary and a secondary. Obviously, we would put the carbocation on the secondary carbon. However, this is hydroboration. So what happens is the boron will add to the anti-Markovnikov carbon, putting the hydrogen here where we would get the most stable carbocation. When we do the oxidative workup, we form the anti-Markovnikov alcohol. So just exactly like an alkene, we're doing the anti-Marconic alcohol. You can see here's the hydrogen that we added. Remember in the first step, the boron would add here. With the oxidation, we remove the boron and make the OH. Now, this is also an enol, isn't it? Because it's an enol, it's not just going to sit there like that. It's going to undergo its tautomerization. What we're going to do is take this hydrogen off, and we're going to put it here. What's that going to give us? An aldehyde. Now, you don't always get an aldehyde with hydroboration oxidation, but clearly if you have a terminal alkyne, double bonds here, carbons 1 and 2, you will form the aldehyde. Very simple tautomerization reaction. Again, we lose this hydrogen, pick the hydrogen up again on this carbon. Yeah?
So an enol is a carbon-carbon double bond with hydroxide?
Yep. Think about the name. It's an alkene and an alcohol. Enol.
So smart.
So smart. Makes sense. It even just makes sense. Any questions? All right. The next group of reactions we looked at were the simple reduction, etc. With alkynes, we have 2 pi systems that we can reduce. There will be 3 different reduction recipes we can use here. If we use our standard hydrogen gas, platinum or palladium, this little /C, that stands for charcoal, carbon. Platinum and palladium are very expensive, as you might know. You don't need a whole lot of it in order to catalyze this reaction. Instead of trying to weigh out a handful of micrograms or something of platinum or palladium, what they do is they take activated charcoal. Has lots and lots of surface area, and they will deposit an atomic layer of platinum or palladium on it. So instead of having to worry about weighing out teeny tiny bits, you just take a teaspoon of the stuff and dump it in. Makes it very, very easy. So this is done on a carbon support. All the carbon does is hold the platinum. And again, we're going to reduce both of our pi systems here and simply make the alkane. So that's simple, just like we did with an alkene, right? We can also use what's called a poisoned catalyst. Instead of putting our platinum or palladium on charcoal, what you do is you put it on barium sulfate. Barium sulfate will attach to the platinum or palladium in such a way that the catalyst becomes very, very ineffective. It's a very, very poor catalyst. It is good enough to add 1 mole of hydrogen, but it won't add 2. Platinum or palladium on barium sulfate will not reduce an alkene. That means that if we start off with an alkyne and we use platinum or palladium on barium sulfate, we're going to wind up with an alkene as our product, and just like with alkenes, the reduction is going to occur cis. That is, both hydrogens come in on the same side. The catalyst that you use is actually called a Lindlar catalyst. That's some guy's name, developed it. So you'll either see this as platinum or palladium on barium sulfate, or simply Lindlar catalyst. Once again, this gives us a cis alkene. Our third mode of reduction is dissolving metal. If we take an alkyne and we do a dissolving metal reduction. Now remember we talked about sodium amide. That's sodium previously dissolved in liquid ammonia. So you put it in, you let it fizz, it stops fizzing, you have a nice strong base. But while it's fizzing and forming hydrogen gas, it's releasing hydrogen radicals. If you do this dissolving metal reduction in the presence of an alkyne, you can actually add those one at a time to the triple bond, and you wind up with a trans alkene. The reason that you get trans stereochemistry is the first one goes on, the thing that adopts the most stable conformation. Most stable conformation will put the alkyl groups far away from each other, and then we add the second. So it's a stepwise radical reaction. You don't really need to know that. What you need to remember is lithium or sodium in liquid ammonia gives a trans alkene. So we have three ways to do this. You can fully reduce it with hydrogen and platinum. We can partially reduce it and get cis stereochemistry with Lindlar catalyst, or we can do dissolving metal and get trans stereochemistry. Any questions? All right, so we will look at examples of that in a minute, but make sure you remember this because these reactions are specific for alkynes. Okay, if we have a carbon-carbon double bond and we react that with acidic permanganate, what happens? Very simply, we split the carbon-carbon double bond, don't we? Now, permanganate is a very strong oxidant. That means that when you use permanganate, you don't get aldehydes. All you get are ketones, carboxylic acids, or CO2, right? We remember that. Well, here, we can't really form a ketone, can we? But what happens with permanganate is we simply split our triple bond, and both of these guys will wind up as carboxylic acids. This half with the benzene ring gives us what's known as benzoic acid. That's this carbon right here. This guy, this 2-carbon, will give us ethanoic acid, or acetic acid is called. So we just split our carbon-carbon double bond. If this happened to have a hydrogen on the end here instead of a methyl group, that's when you would get CO2. So this is even easier than it was with an alkene. We're going to split it, make carboxylic acids or CO2.
The other product will always be acetic acid.
Yep. All right. Now, again, if you looked at the first 2 slides here of this chapter and you see all these reactions, again, it's a little intimidating. What I've tried to do here is to stress that you already understand most of these reactions from alkenes. What you're going to do is sometimes do an addition twice. Remember, when you do the hydration, instead of forming a simple alcohol, you get an enol, and that gives a carbonyl. Reduction we talked about, and again, this is simply splitting the carbon-carbon triple bond. So this is all the new reactions we need to worry about. So let's go ahead and practice some. I will pause here while you diligently write down the products of these reactions. For our first one, we see we're adding HCl to an alkyne. Okay, we say we know this is going to be Markovnikov addition, and we're going to form a 1,1 dihalide. But if we look at this, both of these carbons are the same, aren't they? So it doesn't matter where you put it, but both fluorines must be on the same carbon. Our next one, we're doing hydroboration oxidation. Now we know this is going to give us anti-Markovnikov enol, right? Because it's a triple bond, it's an anti-Markovnikov enol. So we look at our two alkyne carbons. We have a primary and a secondary. Anti-Markovnikov enol. The oxygen must be on the primary. Once we add the oxygen to the primary carbon, remember this is going to rearrange to give us the carbonyl. Way to look at it, this carbonyl used to be the OH of an enol. We simply took the hydrogen off the enol and moved it here. Our next one, we are doing reduction. We have lithium in liquid ammonia. We have an alkyne. We're going to do a partial reduction, aren't we? And wind up with an alkene. Now we know, deep in our heart, that this is going to be a trans addition. But since we have a terminal alkyne here, we can't tell. Simply going to be the appropriate alkene. Any question on these? Our next step. I will say once again, please get really good at doing reactions. Your exam will have 20 of them, and they're worth 3 points each. We look at our first one here. We're doing hydroboration oxidation. We are going to get an anti-Markovnikov enol, aren't we? Now the anti-Markovnikov enol, we look here, we have two secondary carbons. But this is a simple secondary carbon, isn't it? This guy is sitting next to a benzene ring. That's a benzyl carbon. Benzyl, very stable carbocation, right? Therefore, the Markovnikov carbon is the benzyl carbon, so the anti-Markovnikov enol will have the oxygen here. When we do, so initially we will form an enol with the OH here. That will then change, tautomerize is called, into the ketone Again, the oxygen is on the secondary carbon. Hydrogen goes to the benzyl carbon.
Oh, I have a question.
Sure.
I wrote down, which one's a rearranged to give non-hydrogen?
No, because our oxygen is going to be here.
So if it's the
Right.
terminal, it's the other
Yeah, if it's terminal,
Okay.
it will be an alkyne. But otherwise, the hydrogen goes to the most stable carbocation. So it's anti-Markovnikov enol. Our next one here is simple hydration. We have acid, we have mercury. Once again, we are going to form an enol intermediate. With hydration, we get Markovnikov regiochemistry, right? So that means the oxygen is going to go to the carbon that gives the most stable carbocation. We have secondary, we have primary. The oxygen will go to the secondary carbon. So we will form an enol with the oxygen on the secondary carbon. This will rearrange to give us a carbonyl. Because it's on the secondary carbon, this will be a ketone. And our last one here, I love to put this one on exams, mostly because I love to make everybody try to draw the tricyclic structure here.
They're
It's just-
using quotation marks.
It's just really fun to do.
Seriously, that's
Regardless of what we have attached here, we look and we see what's happening chemically. We have sodium amide, so that's sodium previously dissolved in liquid ammonia. It stopped fizzing, okay? Once we add our sodium amide, in a second step, we're going to dump in bromomethane. So what we're doing with sodium amide is we're making the anion here, aren't we? The anion is then going to attack the bromomethane, we'll kick the bromine out, and simply add the methyl group to this carbon. So you have to redraw this part and simply stick a methyl on the end. This is actually not that difficult to draw. You start off with your six-membered ring. We have 3 axial bonds coming up, and then all you do is link them all together across the top. Any questions? All right, this is a classic exam question as well. We have 3 ways of reducing an alkyne. Go ahead and draw the products for dissolving metal, hydrogen, platinum, and carbon, or Lindlar catalyst. All right, our dissolving metal reduction. This is going to give us an alkene, so it's a partial reduction. Because it is radical, it's a stepwise reaction, and we wind up with the trans alkene. Remember, trans is spelled with a capital E. If we take platinum or palladium on charcoal, that's a very powerful reducing agent. It will reduce it twice and go all the way to the alkane. And finally, if we use Lindlar catalyst, Lindlar stands for lousy. We're only going to reduce once, and it's going to be cis. Make sure you understand all three of these. Again, cis is spelled with a Z. We get trans, cis, or full reduction. Any questions?
The middle one's the full reduction one.
Yep. All right, go ahead and run through these. Our first one, we're adding chlorine. It's a triple bond, so we're going to add it twice. If it was an alkene, we would get a trans dichloride. Here we will get a tetrachloride, and it will look like that. Far too many chlorines. Our next one I threw in just to make you realize that this is an alkene, not an alkyne. Just make sure you remember. Here we have HBr peroxide, right? That gives us our anti-Markovnikov alkyl bromide. Tertiary carbon, secondary carbon. It's anti-Markovnikov, so the halogen will go to the secondary carbon. Lindlar catalyst. Lindlar stands for lousy once again. We will get partial reduction, and it will be cis. All right, any questions on the simple reactions of alkynes? Alkyne content you could expect on the exam. There will be nomenclature, and there will be a mixture, like we had here, of alkene and alkyne reactions. At least 20 of them. Your exam will also feature what's known as synthesis. In a synthesis problem, what you do is a reaction backwards. So, you are given a compound, and you're asked to make it from something else. This really is the heart of organic chemistry. Example. What we're going to do is make these four compounds starting with something else. Here are specified we have to start with an alkene. Typically in a synthesis problem, you are allowed to choose any alkene you want. You must put in the reaction conditions, and of course it must work. So let's see how we do this. Let's start off with this guy. We want to make this simple alkyl bromide, right? What you want to do when you do a synthesis problem is, once again, you're going to talk to yourself. You're going to look at this and say, what kind of compound is this? Then you say, how do I know to make that compound, that type of compound, starting with an alkene? All right, what kind of compound is this? Well, it's an alkyl bromide, right? But is the bromine attached to the carbon that would give us the most stable carbocation? No. We have a tertiary carbon right here, right? Therefore, this is it's an alkyl halide, and the regiochemistry is anti-Markovnikov. That means our bromine is not attached to the carbon that would give us the most stable carbocation. So now you look at yourself and say, how many ways do I know to make anti-Markovnikov alkyl halides? Only one. Only one. And that's the radical addition to a double bond, right? It's the only way you know to make it. Our double bond, we're going to put it here. This would be a tertiary carbon, that would be a secondary carbon. In a radical addition, the bromine would go to the secondary carbon. So, you draw your alkene, put in your reaction conditions, HBr peroxide, this gives you this one. Now, is this the only way you could do this? What if we tried this? What if we had our double bond out here on the end? All right, instead of using peroxides, what if I said we could just use HBr? Well, in our alkene, we'd have a primary carbon and a secondary. So you could say, yeah, we could get a carbocation here, and then bromine would add and give us this product. Right? You could say that, couldn't you? But you'd be wrong. Why? Because remember, the ionic addition here has a carbocation intermediate, and it can rearrange. What would happen would be, we would add HBr here. We would form this carbocation. So we put the hydrogen here, we have our carbocation, and we get our famous 1,2 hydride shift. Hydride slides over there to give us the wrong compound. So the only way to make this is like we did, to use our alkene with the double bond through here, and do the anti-Markovnikov addition. Let's do another one. Look at this and say to yourself, what is it? Well, a hydroxyl group in a bromine. It's a halohydrin, isn't it? How many ways do I know to make halohydrins? Only one. That's to add HOBr to an alkene. We know that when we do that, the hydroxyl group will have Markovnikov regiochemistry, which means it adds to the carbon that would give the most stable carbocation. Well, this works because this primary carbon, this is a tertiary. So yes, we can do this with a simple addition of HOBr. These were the carbons of our alkene, here and here. Therefore, it's a halohydrin. carbocation forms at the ring junction. That's why OH adds there. And this is our reaction conditions. Now though, sometimes you or students panic a little bit here and say, oh my gosh, I can never remember all these reaction conditions. How in the world am I supposed to do this? But, remember what I told you about your exam? It's going to have 2 pages, 20 reactions. They've all got the reaction conditions, don't they? So you don't have to remember them really. You just have to go back, refresh your memory by looking at the reactions and then putting them in. HOBR would work. You could do NBS, water DMSO mixture. Either one works fine. How about this guy? Again, we look at it and we say, what is it? Well, it's a trans 1,2-dibromide, isn't it? How many ways do I know to make trans 1,2-dibromides? Only one. And that's to add bromine to a double bond, right? You know that. Where was our double bond? It was between our 2 bromines, so right here. So all you have to do is draw the appropriate alkene and use bromine as your reagent. Any questions? All right, let's look at this guy. We look at it and what do we say? What kind of compound is it? It's an alkyl bromide, right? How many ways do I know to make alkyl bromides? 2. I can do Markovnikov addition of HBr, or I can do anti-Markovnikov addition HBr peroxide. So we look and see what is the regiochemistry. Well, bromine is attached to a tertiary carbon. Therefore, this is Markovnikov regiochemistry. Okay, go ahead and draw an alkene that we could add HBr to and get this product. Well, how about I say we put our double bond down here, in between our tertiary carbon and our secondary. I could do that, right? Addition of HBr, Markovnikov addition, bromine goes to the tertiary carbon. That works, right? But, is there another alkene that would give the same product? What if, instead of having our double bond between the tertiary and the secondary, I simply had our double bond up here between this tertiary and the primary? This guy. Once again, addition of HBr. Bromine would go to the tertiary carbon. And that gives you your product. Is there another alkene that we could do? Instead of having our double bond up here, what if we had our double bond down here? Like that. Would that give us the same product? Well, remember we're going to form a carbocation right here, aren't we? If we form the carbocation here, we can get a hydride transfer, form the carbocation here, add bromine, and we're there. All three of these alkenes would give exactly the same product. These two by direct addition, this by rearrangement of the secondary carbocation to the tertiary. Yeah?
You're saying in the test you would only want one of them, not all three of them?
Well, I don't know, kind of a neat question would be draw all three. But you know, that's just a question. It could be.
How about extra credit question?
That would be good.
Some of us are still struggling with one over here.
All right. Another way.
I have a question. So when it's the anti-Markovnikov, then there's no rearrangement, and then that would not be possible.
Anti-Markovnikov, no rearrangement.
And then we could not draw the third.
Right.
But if it's, we can rearrange them.
Yep. If it's a carbocation intermediate, it will rearrange. All right. This is another way that I sometimes ask synthesis on an exam. I will give you compounds to work with. I will give you a target. And I will say, use one of these to make this. We're going to do this exactly the same way, aren't we? We're going to look at our target molecule and say, what is it? How do I know to make it? And then which of these is going to work? All right, we look at our target molecule. What is it? Well, it's an alkyl halide again, isn't it? How many ways do I know to make alkyl halides? Two. I can do Markovnikov, or I can do anti-Markovnikov. So we need to decide, is this a Markovnikov alkyl bromide or an anti-Markovnikov? You look and you say, is the bromine attached to the carbon that would give us the most stable carbocation? No. No, it's attached to a primary carbon. We have a tertiary sitting out here. So this is an anti-Markovnikov alkyl bromide. All right. Next, you want to look and say, which of these can we add HBr peroxide and get this alkyl halide? Clearly, the double bond must be here, right? It must be out on these terminal two carbons. So the one we want to use is going to be this guy. Bromine has to go to the end. This had to be our double bond. These two don't have a double bond out there on the terminal carbon, so they don't work. Only this one would work. And our conditions. Once again, if you don't remember them, go look at your set of reactions. They're all going to be there. This is just HBr peroxides. Any questions? What kind of compound is it? It's an alkyl bromide. What's the regiochemistry? Anti-Markovnikov. We have to add to the terminal carbon, so our double bond had to be there. Only one possible choice. Let's do another one. What if I asked you to make this tertiary alcohol? We look at it and we say, what kind of compound is it? Well, it's a tertiary alcohol. How do I know to make alcohols from alkenes? Two ways. Markovnikov, simple hydration, or anti-Markovnikov, hydroboration oxidation. So we need to look at our regiochemistry. The hydroxyl group is bonded to the tertiary carbon. That carbon would be the most stable carbocation. So this is Markovnikov. We're going to do this either by simple hydration or by using mercury 2 acetate, and then bisulfite to get rid of the mercury. All right, we need to choose an alkene. We are going to add it to our tertiary carbon here, right? We have two carbons here that have double bonds attached to the tertiary carbon. So we could take this guy, do simple hydration to get our tertiary alcohol. Our first one, this guy, this guy. If we simply did acid catalyzed hydration, we would get the carbocation here. Or this guy, we would get the carbocation here, again at the tertiary carbon. And why does this one work? Because we would form the secondary carbocation, which would rearrange to give the tertiary carbocation. So all three of these work to give the same product. Let's do one more with this set. Oh, this is just the more civilized way to do this. Here we have mercury 2 acetate. We reduce it off, again, to make the tertiary alcohol. With mercury 2 acetate, however, because we don't have rearrangements, only these two guys will work, not this one. Remember, mercury 2 acetate, no rearrangement. Simple hydration, lots of rearrangement. All right, you do the talking to yourself. What kind of compound is it? Is the halogen attached to the carbon that would give the most stable carbocation? Nope. Therefore, this is anti-Markovnikov. Pick an alkene and put in your reaction conditions. We must pick an alkene where we can put the bromine here on our secondary carbon. This is the secondary carbon, but this half would be Markovnikov relative to this carbon, wouldn't it? Here we have a tertiary carbon, secondary, so the anti-Markovnikov regiochemistry would be here. Here, anti-Markovnikov would be up here on the primary. So, since we have to add to the secondary carbon, that's this guy, the only one that's going to work is going to be this one. Here is our compound, our reaction conditions, simply HBr peroxide. Synthesis can really be fun. By the time you finish the second semester of organic, you will be doing synthesis reactions that are 2 to 3 steps. So you start off with something, you do something, make one compound, do something else, make a second compound, and do your final step to get your compound. So that's what's coming if it's done right. Another one. Here we have a simple alcohol. You know what to say to yourself. What is it? Well, it's an alcohol. It's a primary alcohol, isn't it? Is this going to be Markovnikov or not? I know 2 ways to make alcohols. I can make Markovnikov or anti-Markovnikov alcohols. Here we have a tertiary carbon. Here we have a primary carbon. This is anti-Markovnikov. Pick an alkene and put in your reaction conditions. Hydroxyl group has to go to our primary carbon. We look at our selection up here. We need the primary carbon to be part of an alkene, don't we? This one is not, this one is not. Only this guy will work. So you want to draw this as your starting material. How do we make anti-Markovnikov alcohols? Hydroboration, oxidation. So what you write on the test, here's our starting material, our reaction conditions, hydroboration followed by peroxide in base. Do this one by yourself. What kind of compound is it? Well, it's an alkyl halide. We know how to make Markovnikov and anti-Markovnikov. Which one is it? Well, the bromine is on the tertiary carbon, so it is Markovnikov regiochemistry. Which one of these guys can give us a Markovnikov alkyl bromide? We have to put the bromine on the tertiary carbon. So here's our tertiary carbon, this one and this one. However, we remember that the addition of HBr Markovnikov style will proceed with rearrangement, bless you. So actually, all of these are going to work. This one and this one would add directly. This we would add and do rearrangement. All we need to show is HBr. Now remember, this exam covers reactions of alkenes and alkynes. So let's expand our selection here to include a nice variety of potential starting materials. What we want to do is make this 1,2-diol using one of these guys. Now this really isn't so difficult. We're looking for a 4-carbon unit, aren't we? Well, you kind of want to look up there, and these things with a ring you can just forget about, right? All right, 1,2-diol. If you look at this, hydroxyl groups are nicely next to each other, aren't they? So let's call this a cis 1,2-diol. How do I know to make cis 1,2-diols? Well, we can make a cis 1,2-diol simply with permanganate or with osmium tetroxide. We see up here we have 2 potential alkenes, don't we? They're both 4-carbon. One is trans and the other is cis. So which one do you want to use? Well, let's look here. How about our methyl groups? Are they cis to each other or trans? They're trans. Methyl groups are trans to each other. Therefore, our 4-carbon backbone, trans-methyl double bond, we're looking at these 3 compounds have 4-carbon backbones. Obviously, the alkyl bromide we can forget about. We want trans-methyl groups. Only this guy is going to work. Now our reaction conditions. Again, if you forgot, go look at the reactions. There'll be 20 of them. We simply need to add either permanganate or osmium tetroxide. Any questions? We're making an aldehyde. How many ways do we know to make aldehydes? Actually, we do know 2, don't we? We can do ozonolysis of an alkene and split it, or we can do hydration of an alkyne to give an enol, which could then form an aldehyde. All right, so this guy is an aldehyde. Again, we know 2 ways to make it. anti-Markovnikov hydration, or ozanolysis. I say anti-Markovnikov because in this carbon chain, this is attached to a primary carbon. This has a secondary carbon in it, so this would be anti-Markovnikov regiochemistry. All right, we have a 3-carbon backbone, don't we? We are looking for something that we can hydrate or that we can split with ozone. Let's see. My gosh, there's only one that's going to work, isn't there? Only one 3-carbon backbone in this whole mess. Our reaction conditions. We have to do an anti-Markovnikov hydration. That's just going to be BH3 followed by oxidative workup.
And do you have to remember all that?
Have to remember all this
Like
stuff?
all these, the reaction.
No, again, look at your exam. We're thinking exam mode here. You've got 20 reactions on your exam page. If you forget the exact conditions, just turn it over and look it up.
Okay.
Carboxylic acid. How many ways do we know to make carboxylic acid? We know 2. We can use permanganate on an alkene or permanganate on an alkyne. We have a 1, 2, 3, 4 carbon unit here. We're going to oxidize either an alkene or an alkyne with permanganate. 4-carbon unit is actually 2-methylbutane. So let's look up top and see if we can find an alkene or an alkyne that has this 4-carbon backbone. Well, clearly, these guys aren't going to give it to us, are they? These are all, well, this is cyclic. We have 2 alkynes left. If you look at this one, this is the 4-carbon backbone twice. This doesn't have enough carbons for our backbone, so only this guy will work. What we want to do is simply split this little guy in half with permanganate. So, there's our starting material. We are simply going to dump in acidic permanganate, split it right down the middle into 2 moles of our carboxylic acid. Our next one, different assortment here, and we're making a methyl cyclohexanol. All right, what do we say to ourselves? What kind of compound is it? Well, it's an alcohol. The OH is bonded to the tertiary carbon, so it's a Markovnikov alcohol. We need a 6-membered ring backbone and a methyl group. How do we know to do this? Simple acid-catalyzed hydration would work. We can also do mercury 2 catalyzed hydration. So let's look up top. We're looking for 6-membered rings. We have 2 methyl cyclohexenes up here. Remember, we need access to our tertiary carbon. This is the most direct answer. If we simply took this and did hydration, we would get the tertiary alcohol. Now in reality, we could have also used this, couldn't we? And it would have just rearranged itself all day until it finally got here. If we had used mercury 2 acetate, this is the only one that we could use. Couple more things here. Let's go ahead and do our next alcohol. Again, what is our regiochemistry? Is it bonded to the most stable carbocation? Absolutely not. So this is anti-Markovnikov. How many ways do we know to make anti-Markovnikov alcohols? Only by hydroboration oxidation of an alkene. Again, we need a cyclohexane backbone. So we're down to these 2. Which of these would you pick? If we use this guy and did hydroboration oxidation, we would get our hydroxyl group here, no problem, right? If we use this one over here, the hydroxyl group could go here or here. This is a much cleaner solution. Again, reaction conditions, hydroboration, oxidation. Our last one. We are making an alkyl halide. What's our regiochemistry? Is the halogen attached to the carbon that would give the most stable carbocation? Absolutely not. This is a benzyl carbon from. It's a benzyl carbon. Of course, it's going to give the most stable carbocation. So this is anti-Markovnikov. How many ways do we know to make anti-Markovnikov alkyl bromides? HBr peroxide. Our compound must have our benzene ring, and we must have a double bond. We look up top. We have 2 potential compounds. Remember, we also need this methyl group dangling out. This one has it, this one does not. Only this guy is going to work. And our conditions, simply HBr peroxide. Now you see how fun synthesis can be.
Would I have used hydroboration oxidation?
Hydroboration oxidation would give us an alcohol, though. Right, we need the alkyl halide, so it's got to be HBr peroxide. Only way you know.